In this video, we are going to learn about design of shaft, key and coupling, especially about flange coupling. Before learning the design procedure, we should know the reason and application of using shaft, key and coupling. Now let's learn about shaft. A shaft is an element used to transmit both the power and torque. Moreover, shafts are made in different shapes and forms, but most of them have a circular cross-section. A shaft may simply connect to another shaft via coupling. Shaft can carry gears, pulley and sprockets in order to transmit rotary motion and power via mating gears, belts and chains. Two shafts can be connected together via coupling mechanism. As we can see, as many as applications of shaft in automobile industry. The engine power is transmitted to the wheels through differential. Let's learn about keys. A key is a piece of metal used to connect a rotating machine element to the shaft. A key prevents relative rotation between two parts and may enable torque transmission. In simple words, key ensures that the shaft does not slip from the coupling. A keyway and key set is important for a key to function properly between shaft and rotating elements. In this picture, you can clearly see the key, keyway, key set. Now for a better understanding, let's see an animation video. Now let's move to the topic of flange coupling. In flange coupling, each flange is mounted on the shaft end and keyed to it. One flange has a projection and the other has the corresponding resist. This is to maintain the alignment. Both the flanges are coupled together using bolts and nuts. There are three types of flange couplings. Those are unprotected, protected and marine type flange couplings. We'll learn only the design of protected type flange coupling. In protected type flange coupling, the bolts and nuts are protected by the flanges on two halves of the coupling to avoid danger to the workman. Now let's see an application of coupling. In a domestic generator, we see that a shaft is rotated by an engine by converting chemical energy of fuel to mechanical energy. This rotation of shaft of engine is connected with the shaft of an electric alternator, which converts mechanical energy into electrical energy. This is done with the help of coupling.
So guys, moving on to the design part of the shaft, the ultimate goal is to find out the diameter for the given parameters. So to deal with it, we have got some important formulas. So let's see them. So the first formula is the ultimate formula through which we will find out the diameter of the shaft, which is our ultimate goal, which requires the shear stress. So tau represents the shear stress, which you will see in the following video, and the term Te represents the equivalent twisting force acting on the shaft. So now what is this equivalent twisting force? We have got a formula to find this out, which involves the torque on the shaft and the moment on the shaft. And this is all about it. Now you can see the individual terms here. Okay, now let's move on to a problem to understand it better. So in this problem, it is given that a shaft is supported on two bearings 750 mm apart, and the shaft transfers a power of 15 kilowatt and at speed 200 rpm, which we will require in order to find out the torque. Now it has two gears attached to it, a pinion having 30 teeth of 5 mm module and a gear having 100 teeth of 5 mm module. So to imagine this better, we'll see it in a diagram. So the pinion is located to the left of the right hand bearing at 100 mm, at a distance of 100 mm, and the gear, which is represented as C, is located 150 mm to the right of the left hand bearing. The problem clearly states that the pinion delivers power horizontally to the right, and the gear receives power in vertical direction from below. So these are the factors where we'll be finding the bending moment further. And ultimately, the allowable or the maximum shear stress is given as 54 Newton per mm square that we would require to find out the suitable diameter of the shaft. So now moving on to solving this problem. Initially, I've just written the number of teeth as in the pinion as ZP and MP, the module of the pinion, which is 30 and 5 mm respectively, and the number of teeth on the gear, which is 100, and the module again, which is 5 mm, and I've represented as G here. So the first step is to find out the torque, and this formula comes from the power formula, where P is equal to 2 pi NP by 60. So this way we find out the torque, which is 716.19 Newton meter, and this torque we will require in finding out the equivalent twisting force. So now again, moving on to the next step, we know that module is equal to diameter by the number of teeth. So in this way we could find out the diameter of the pinion as well as of the gear. So as in the diagram, I have represented pinion as C and gear as D. So it comes here, FTC. As we know, force is equal to torque by radius. So the force acting on the gear, which is FTC, is equals to 2865 Newton, and the force acting on the pinion, which is FTD, is 9549 Newton. Now since we know the horizontal and vertical forces acting, let's go on to find out the bending moment. And we need to, obviously, since there is both the vertical and horizontal, we need to find the resultant at the end. So now moving on to the next step, to find the horizontal load, it'll be better if I show you with the diagrams here. Yeah, okay. So here RA plus RB, the resultant RA and RB, which is acting to the opposite direction of the horizontal load, is equal to the horizontal load, which is 9549 Newton again. So now considering one point, for example RAH, now we know that RBH into the distance from A point, which is 750 mm, is equals to the force 9549 into the distance again, which is 650 mm. In this way we'll find out the RBH. H represents horizontal, RA and RB are the reactions. So in this way we'll find out the RBH and RAH, and using RBH and RAH we'll find out the moment acting horizontally on both gear and pinion. It acts on both the things, but only thing is the magnitude will differ. When it's acting horizontally, the magnitude of the pinion is higher because it is going to transmit the power in horizontal direction. While acting vertically, the gear moment will be higher, since it is getting its power from the vertical direction. So now similarly we move on to find out the vertical load, which is as similar as the horizontal. We have two reactions which is equal to 2865 Newton, and then choosing a point A, multiplying the distances, and finding out the RBV, which is vertical, RAV again vertical, and then ultimately finding out the moment acting at C with the vertical load and acting at D, which is the pinion vertical load. As I said before, the vertical moment will be higher for the gear and horizontal moment will be higher for the pinion, because that is what they do. Now moving on to finding the reactions. The reaction at C will be equal to square root of mcv square and mch square, which is the gear's vertical square plus gear's horizontal square, horizontal moment. Both vertical and horizontal moment will give you the resultant bending moment at resultant moment at the gear, which is equals to 393,268.79 Newton mm. And similarly for the pinion, now here we could see that the moment at the pinion is higher, so we take the greater value obviously, so that the shaft never fails. In the design we'll always take the maximum value so that the shaft never fails, and then only it will be considered as a safe design. So now the resultant moment is equal to 829.561 Newton meter. Moving on to next step, we'll find the equivalent twisting force using the formula, and which is equals to 1095.951 Newton meter. And now ultimately finding out the diameter of the shaft. Since we know all the parameters, we know the equivalent twisting force and also the allowable shear stress which is given in the question. We'll find the diameter of the shaft, which is going to be equal to 46.9 mm. So roughly this is going to be taken as 50 mm. You could also use various design data books and and you can check for the standard values over there. If you go via design data book, you will find the value as 48 mm, but here I have roughly considered it to be 50 mm. So now this is how we have designed a shaft, and this design is safe. So now moving on to the design of a key. So what is a key and where do we use keys were previously explained in this video. But now for the key, what do we need? It's a three-dimensional thing. So you would need a width, you would need the height, and you will need the length. So the width and the height will be calculated using the diameter of the shaft, which will be known to us, or we'll calculate that also. And for this one we would need a design data book, which was previously introduced in the slides. Our reference was put there, so you can check. And ultimately we need to find out the length. So how do we go? Let's check out the important formulas. So first one is with the shear stress. So now here there are different parameters given here. For example, this torque, D for diameter and W for the width, and tau K is the shear stress acting, or the maximum shear stress on the key, into L by 2, which is length. So ultimately you have to reframe the formula and find out the length. And next, using the crushing stress. So there are two stresses acting on the key, which is the shear stress and the crushing stress. So moving on to the crushing stress, here again you will have instead of width you will have here the thickness, which is the height. Height is considered as the thickness, so it's all the same. Height and thickness is the same, which we will find out through the design data book. And the sigma K is the crushing maximum or the allowable crushing stress for the key or on the key. Yeah. So now let's check out a problem. So design a rectangular key for shaft of 50.5 mm diameter. The shear and crushing stresses for the key material are 42 megapascal and 70 megapascal. So the megapascals are nothing but Newton per mm square. Yeah. So the first step I've done is listed out the given datas, And then from the design data book, using the diameter of the shaft, I have found out the width and the thickness or height, whichever you can call, and the reference page number is 5.21 in my reference design data book. So now you need to calculate the torque. And how do you calculate the torque? You know the shear stress of the material and you know the diameter of the material. So using the previously used formula for the shaft, you can find out the diameter, which is in Newton mm, since all other data are in mm. Now moving on to the now considering the shear stress, we find out the length. We reframe the formula which we saw in the previously in the video, and we find out the length, so which is equal to 62.59 mm. Now using the crushing stress, again we need to find out, because our key should never fail, and we should always choose the maximum length between the two. So when using the crushing stress, I found out the key's value to be 120.1, the length to be 120.17 mm. So now considering the maximum value, and again going back to the design data book to get the standard length values, from the design data book, page number 5.22, the length is equal to 125 mm, and this is totally safe. Your system is safe, your key is safe, and this is how you design a key.
Let us see the design procedure for flange coupling. The design procedures are as follows. The first step is to find the diameter of the shaft, which is small d cube is equal to 16 into t divided by pi into tau. Second is to using this d, we can find the diameter of the hub, which is capital D is equal to 2 into small d, and then the length of the hub, which is L is equal to 1.5 d. Then the thickness of flange, which is TF is equal to 0.5 d, and finally the protective guard thickness, which is TP is equal to 0.5 into small d. The third step is to check shear stress for the hub. The formula for this is T is equal to pi by 16 into capital D power 4 minus small d power 4 divided by capital D into tau f. The fourth step is to check shear stress for flange, where the formula is T is equal to pi into capital D TF into tau f into capital D by 2. The fifth step is to check stresses for the key. Here we need to find both shear stress and crushing stress. So the shear stress T is equal to L into W into TK into D by 2, and the crushing stress is T is equal to L into T by 2 into sigma CK into D by 2. Now we check the shear stresses for bolts. The shear stress is T is equal to pi into dB square divided by 4 into tau b into N into dP by 2, and the crushing stress is T is equal to dB into TF into sigma CB into N into dP by 2. Now let us look at a problem. Design a cast iron protective type flange coupling to transmit 15 kW at 900 rpm from an electric motor through a compressor. The service factor may be assumed as 1.35. The following permissible stresses may be shear stresses for shaft, bolt and key. The material is 40 megapascal, and the crushing stress for bolt and key is 80 megapascal. So we'll go step by step. First, we find the diameter of the shaft using the formula d cube is equal to 16t by pi tau, where we get the answer as 32 mm. Next, we check the shear stress for hub, where 4.45 megapascal is less than 8 megapascal, so the stresses for the hub is safe. Third step is to check shear stress for flange. Here also 2.08 is less than 8 megapascal, so it is safe. Fourth step, we check the stresses for the key. W and T we get the values from the design data book, and the shear stress is also safe here since 27.98 is less than 40 megapascal, and the crushing stress is also safe since 69.94 megapascal is less than 80 megapascal. And the fifth step, we check the stresses for bolts. Both shear stress and crushing stress are safe, since for shear stress 24.99 megapascal is less than 40 megapascal, and for crushing 9.82 megapascal is less than 80 megapascal.